We now want to address the issue of work done by non-conservative forces and how that changes the energy of an object. Now, at first glance, what we can say is that when I have work done by a non-conservative force, okay, so the classic example would be, maybe something like friction or air resistance, okay? So in the case of something like friction or air resistance, when you have a particle or an object starting out with a given amount of total mechanical energy, these types of forces will typically reduce that total amount of energy. Okay, but these are not the only types of non-conservative forces that do work, right? You can give a generic push to an object and speed it up, and things like that. So this whole idea of non-conservative forces doing work just means that the energy can either be put into the system as a result of the work, if it's a push, or it can be taken out of the system in the cases of things like friction and air resistance, or what we would call dissipative forces. But at the end of the day, what happens is that when I have a non-conservative force and that does work on an object, okay, that will change my mechanical energy. Okay, so work done by non-conservative forces changes your mechanical energy. So what this does is this changes the sum of your potential plus your kinetic energies. Okay? And so what this means is that work done by non-conservative forces is going to be equal to the change in these. So this is going to be U final plus KE final minus U initial plus KE initial. Okay? And so if I rearrange this, what this gives me is that U initial plus KE initial plus the work done by my non-conservative force is going to equal my final potential plus my final kinetic. Now remember that the final, potential, I should say, the potential and the kinetic, these are your mechanical energies. And thus, your U will have components due to gravity, or elastic, okay? So U grav and U elastic, your potential energy will be split, your mechanical potential energy will be split up between these two parts. Okay? But this is the basic statement of conservation of energy with the application of non-conservative forces. Okay? So when I have non-conservative forces doing work, this is what will happen. Now remember that work can either be positive or negative. Because, remember that work is equal to force dotted into displacement if you are dealing with constant forces, or this is the integral of f dot dx. Okay, if your force is not constant. Okay. So let's look at a quick example here, and to start, let's start out with a flat plane, and I have a block, and let's say that the mass of the block is equal to, for kicks and giggles, 1.5 kilograms. And I give it an initial speed in the x direction. And by the way, let's go ahead and define a coordinate system. So along the plane is the plus x direction, Normal to that will be the y direction. This is minus y, and this is minus x. Okay, so we've got our coordinate system. We're going to give the initial speed, the initial velocity in the x direction, if you will. Let's give this 20 meters per second. Okay, and let's say that there's a coefficient of friction between our surfaces. This is kinetic friction since it'll be sliding, and let's just say 0.25. Okay, so now here's the question. I want to use this concept of change in mechanical energy as the work done by my non-conservative force to find out how far the block will need to go for the final velocity to be 0. Okay. Now, obviously, we can do this from a Newton's law standpoint, right? We can calculate the frictional force acting on the block, and we would be able to then calculate the acceleration, and we could plug that into the third kinematic equation. Okay, so that's one way to go about this, but we want to do this directly from the work energy stuff. So we're going to claim that our work done by our non-conservative forces plus my kinetic energy initial plus my potential energy initial is going to equal my potential energy final plus my kinetic energy final. Okay? Now, first of all, if this is a flat plane, you'll note that we can just as easily claim that our gravitational potential is 0. And since it's moving over a flat surface, our final potential energy is 0. And we can do this with impunity, okay? There is no change in potential energy gravitationally here, and since we're not connected to any springs, there is no elastic potential energy. So we can set both of these equal to 0. And when you don't have changes in potential energy, you just recover the work energy theorem, right? And so now we're going to have 1/2 mv initial squared plus the work done by friction. So this is my frictional force, my kinetic friction force, times, technically, dotted into the displacement vector. Okay? And this is going to equal my final kinetic energy, but if I'm claiming that my final kinetic energy is 0, then this is also 0. Okay? So the whole goal here is to solve for delta x. All right? The whole goal here is to solve for delta x. So now we need to look at this work done by our non-conservative force, our frictional force, in a little bit more detail here. Okay, so I've got my kinetic friction force, and we're going to dot that into our displacement. And so in vector form, F sub k is going to be equal to mu k times mg, right? The coefficient times our normal force. But because my block is sliding in the plus x direction, this frictional force is in the minus I direction. Okay? And delta x is equal to, the vector delta x is equal to delta x in the I direction. And therefore, the work done by this is going to be negative mg, I need the mu k in there. and this is in the I direction. Okay. Oh, nope, 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 nope. This is the dot product. It's a scalar. And so this is going to be mu k mg times delta x. That was the part I was missing. There we go. Okay, so now we're ready to plug this in. 1/2 mv naught squared minus mu k mg times delta x equals 0. And if I solve this for delta x, well, we can see that the m's are going to cancel out. I still don't really have to worry about my masses here. In general, when you don't have springs, that will be true when working with forces and energy. Okay, if you're not dealing with springs, then your masses are typically going to cancel out. And so if we solve for delta x, I'm going to get v naught squared over 2 times mu k g. Okay, and let's just check the units here and make sure that our units balance out. So up here, we've got length per time squared. This side is length. And down here, we've got length per time squared. So as you can see, I've got a length squared per time squared in the numerator from my velocity, and I've got length per time squared from the denominator from g, and this does indeed boil down to length squared per time squared, and then if I multiply that by the reciprocal, this is time squared over length. Then my time squareds cancel out, this length cancels with one of these lengths, and I'm left with length, which is what I want on the left side. So the units check out. Okay. Now, I'll leave it to you to plug in the numbers, but this isn't a terribly difficult calculation, okay? But that is the algorithm. And remember, okay, remember that G here is just 9.8. It is not negative 9.8. This is something that a lot of people struggle with is remembering when to put in the negative. So the negative, when you put the negative in, that is specifically when you're analyzing things from the force or from Newton's laws perspective, okay? But the negative sign has already been implicitly put in here, okay? And the reason is when I apply Newton's second law to the block, right? So let's do it on a new slide. This one's getting pretty busy. So if I look at my block and I draw the free body diagram of the block, we have the weight down, and I'm assuming the same coordinate system as the previous slide, right? And we have the normal force, and in this case we would have the friction force acting this way. And so in the vertical direction, the sum of all my forces in the y direction is Fn minus mg. So this minus sign is already taking in the negative part of g into account. Okay, so then when we claim that the normal force is equal to mg, we've already taken that minus sign into account. So I don't need to put in minus 9.8 into this calculation. I already put in the minus 9.8 right here, minus 9.8, and then when I move it over to this side, the g becomes negative or positive. Okay, so just a note about that. Okay, so let's do a little bit more of a sophisticated example here. So we'll do two more examples. And in this case, let's look at a ramp. Okay, So my block is going to start at the top of the ramp from rest, and let's let this be 30 degrees, and let's let this be 2 meters. Okay. And the ramp has a coefficient of static friction of 0.2. And once again, let's let the mass of the block be 1.5 kilograms. Okay, so here's the question. When we release the block, what will the speed of the block be at the bottom of the ramp? Okay, what will the speed of the block be at the bottom of the ramp? So we want to do this from the work energy considerations. So the work done by my non-conservative force, well, let's just write it out from the beginning. U initial plus KE initial plus the work done by my non-conservative force is equal to my potential final plus my kinetic energy final. Okay? So, first things first, when we walk through this, once again, we're going to have U grav initial. We could potentially have U elastic initial. And we can have U grav final and U elastic final. Okay? Now, first things first, we do not have any springs in this problem, so there is no elastic energy. Everything is just gravitational. But I do have MGH initially. Okay? But I don't have any kinetic energy. And then this is also going to be my frictional force dotted into my displacement. And I don't have any gravitational at the bottom. But I could be moving. So this is going to be 1/2 mvf squared. Okay. Now, as we've done before, what we're going to do is we're going to orient our coordinate system such that I have this. Okay? So when I do that and I draw a free body diagram in this coordinate system, that's X. Okay. So when I draw the forces that are going to be acting on my block, gravity is down. The normal force is up this way. Friction is acting this way, or will be acting this way. And as a result, what we have from our gravitational force, I have mg cosine theta right here. Where this is theta. And this is also theta. Okay. And we have mg sine. Okay. So the work done by friction, right? my frictional force is going to be given by my coefficient, now times my normal force, but in this case the normal force is mg cosine theta. And again, this is in the minus I direction. Okay? So, putting all of this together, when I insert this in for my frictional force in the work, what this becomes is mgh naught plus negative mu k mg cosine theta, all right, times delta x, whoops. And the dot product behaves the exact same way as the previous part. Okay, the negative I dot I becomes negative 1, and that's where this negative sign is coming from. Okay, and all of this is going to equal 1/2 mv final squared. Okay, so there's a couple of things we need to do before we solve for everything, but the first thing, once again, the masses cancel out, and so this is g h naught minus mu k g cosine theta delta x equals 1/2 bf squared, right? And then the last thing we need to do, because we know g, we know h naught, we know mu k, we know theta, we need to handle delta x now. And so delta x is the distance down the plane. Okay? And that is in the I direction. And so I guess I implicitly implied that, but yeah. So delta x is going to be equal to the magnitude of the length of the plane in the I direction. So I really should explicitly state that, so that when we do this dot product, we can see that the minus I times I goes to negative 1. And so, if my angle is 30 degrees and my height of the ramp is 2 meters, then we can use trigonometry to show that the length of the ramp is 4 meters. Okay? And therefore, now we've got delta x. And so now it's just solving for VF, so multiply everything by 2. And then VF is the square root of this. Okay. Now, when you have a problem like this, whenever you have a square root with terms like this, it is possible you could get an imaginary number. If you get an imaginary number, what does that mean here? Well, it means that the block didn't reach the bottom. It stopped somewhere on the ramp. The friction stopped it on the ramp somewhere before. Okay, so one way to check is just to kind of get an estimate of whether or not this is going to be a imaginary number or not. And so what we can do is we can say, okay, just to get a glimpse, okay, so this is 2 times 10 times 2, and I'm dropping the units for brevity, all right? But how does that compare to 2 times 0.2 times 9.8 times, now the cosine of 30 is 0.866, and then times 4. Okay? So in other words, is this number larger than this number? Right? Well, this number is obviously 40. Just to be consistent, since we're doing an estimate, let's make this 10. Okay? So the first number is 40, or at least approximately. Okay, so 2 times 10 is 20, times 4 is 80, but 80 times 0.2 is what? 16? 16 times 0.866. So this is going to be something around 14, maybe 13 or 14. Okay, so even if my estimate here isn't exact, it still shows that 40 is much bigger than 14. So this is going to be a positive number. So the block will reach the bottom. Okay, and then I'll leave it to you to plug in all of the numbers exactly. Plug in 9.8 for 10 or for G, and then do the calculation explicitly. But you should be able to come up with a number. Right. And as our last example, do the exact same thing. Okay? But this time, once the block reaches the bottom, there's a spring it can compress. Okay? So once again, let's say that the coefficient of friction is 0.2. This is 2 meters. This is 30 degrees. The block is 1.5 kilograms. And my initial velocity is 0. Okay, so now here's the question. Once it reaches the bottom, okay, the coefficient of friction goes away. So once it reaches the bottom of the ramp, it'll just continue to slide, and then it'll compress this spring, okay? So the question is, what is the maximum compression distance? Okay? And so the setup is going to be very similar to what we had before here. Okay? It's going to be very similar, except now we're going to have elastic thrown in here. Okay? So our total energy calculation is going to look like this. U grab initial plus U elastic initial plus KE initial plus the work done by our frictional force. So since this is friction, I'm just going to go ahead and put work done by friction instead of non-conservative, because that's a very generic term, and here we're specifically dealing with friction. Probably should have done that earlier, but it is what it is. Oh, that's it. Right? Okay. So, now we've got our entire conservation of energy equation written out. So now we go through it term by term. Okay, so at the beginning, I'm going to have MGH. I'm not connected to a spring yet initially, so my elastic potential energy is 0. I'm not moving yet, so my kinetic energy is 0. And I'm going to have negative mu k mg cosine theta delta x, just as before. All right. And now, instead of calculating, well, okay, so first things first, U graph final is 0 since we're at the bottom. At the point of maximum compression, this is when the spring brings the mass to rest. So at the point of maximum compression, there is no kinetic energy left. Okay? And I will have my elastic spring left over. So this is going to be 1/2 k times x squared. And so the delta x here is the distance down the ramp. And the x here is the distance the spring has been compressed. Okay. And so, if I want to find the distance of maximum compression, then this is what I'm solving for. Okay, I'm going to solve for this x right here. So, if we do that, we need to multiply everything by 2. And then we need to divide by k. Okay? And notice that my masses have not canceled out this time. And so here k is the spring constant, not the subscript k on our kinetic friction. So it is unfortunate that some of these variables keep getting recycled, but this is the way it is. Okay. And then I need to take the square root. So you'll notice this is a very similar calculation to before. And so because we ensured in the previous problem that the root would be positive, or the calculation under the root was positive, then this is still going to be positive because I'm multiplying both terms by m. So it'll still be positive, and then I need to divide by the spring constant and then take the square root. Okay. So again, I'll leave you to do the calculation, but it would just be written out as 2 times 1.5 kilograms times 9.8 meters per second squared times a height of 2 meters minus 2 times 0.2. Coefficient of friction is unitless, by the way. 1.50 kilograms times 9.8, times 9.8 meters per second squared times the cosine of theta, which is 0.866, times delta x, which is 4.0 meters. And then I'm going to take all of that. Ooh, let's see if we can make that a little bit straighter. It's a little bit better. Divided by 100 newtons per meter. Okay? So there you go. And all of that is under the square root. Okay? All of that is under the square root. There we go. All right. So there is some examples with non-conservative forces and how it affects your total mechanical energy. We didn't do any examples of where our particle gains energy as a result of our forces, the non-conservative forces. But in most mechanical systems, they will be dissipative. Okay. Now you can absolutely have system or individual forces that do provide energy into a system, things like thrust, but in general, for a lot of mechanical systems, they will be dissipative. Okay, so I hope that this helps give you some guidance on work with non-conservative forces and its connection to mechanical energy, and we will see you in the next video.